Welcome back, and this is the last in the series of videos looking at buffers. So in this video we're going to be looking at indicators and how indicators change their colour in acid-base titration. We're also going to be looking in more detail at acid-base titration curves and at the end point of these titrations. So you're going to need your notes, and we're starting on page 13. So an indicator is simply either a weak acid or a weak base which has different colours in its undissociated and its dissociated form. So if we think about an indicator as being an acid, you've got hydrogen ion, which makes it an acid, and the IN part, the salt part. So when it's in this form it's red, and this form it's blue. Now if we add excess hydrogen ions, that's going to shift the equilibrium position to the left hand side, and we are going to see red. So because you've added excess of these, it shifts it this way. Now if we add excess OH negative ions, a reaction is going to go on. So the hydrogen ions are going to react with these extra OH negative ions to make water. And that's going to have the effect of reducing the concentration of the hydrogen ions. So this time the equilibrium position is going to shift to the right hand side, and we're going to see blue. So the end point of the titration is, yes, where the acid and the alkali have reacted completely. In other words, I've used up all my acid and I've not added any excess alkali. So the ideal indicator for a given acid-base titration is one that changes colour at the equivalence point. You don't want it to change too early or too late, but over that vertical section of the graph. So just like any weak acid, we can write the K value for it, the equilibrium constant value. We call this KIN because we're talking about an indicator. But it's the same expression, concentration of hydrogen ions times by concentration of the IN part divided by concentration of the undissociated acid. Rearranging that to make hydrogen ions the subject, we get KIN times the concentration of the acid divided by the concentration of the salts. Negative. So in the middle of the indicator's colour change, these two are present in equimolar concentrations, equimolar solutions, so then they cancel again, and we get the fact that the concentration of hydrogen ions is equal to the KIN value. So it gives us pH is equal to KIN. So in other words, we want the pKIN of the indicator should be as close as possible to the pH at the equivalence point of the titration, because at this pH, this equivalence point, then the indicator is halfway through its colour change. You don't need to learn any of the indicator names or colours. You do need to know their colour at the equivalence point at the end point, but not their colour in acid or alkali. That is given to you in your data book. But here are some common indicators. And you may have wondered at GCSE or last year why we choose particular indicators for particular acid-base reactions, and that's because they actually have different equivalence points. So methyl orange has quite a low equivalence point of 3.7, whereas phenolphthalein is quite high, it is 9.1. So when we have a strong acid and a weak base, we would usually use methyl orange. But if we have a weak acid and a strong base, we would normally use phenolphthalein. If we get these two round the wrong way, they will change colour over the wrong section of the graph. So on page 15, we're going to sketch 4 graphs. We're going to sketch the strong acids with the strong bases and the weak acids with the weak bases, and so on. It's important that you can sketch these and you can use information from the question to plot various points. So a strong acid, strong base looks like this one. Starts at about pH 1. There is a long vertical section of about 5 pH units. The end point, the equivalence point here, is pH 7, and it finishes at around about pH 13. Do watch the volume. It should match the data given in the question, but that is a strong. A weak acid versus a strong base, however, looks a little bit different. Same sort of shape, but different starting points. So because it's a weak acid, it starts around about pH 3. The end point, the midpoint of this vertical section, is around about pH 9. It only covers about 3 pH units, but it still finishes about 13. Okay, and this is an important part. This is your buffering region, as we said in the previous video. And that region, you've got excess acid because you haven't neutralized all your acid, and you've made enough of a salt to become a buffer. But notice the equivalent points is now no longer 7. So for a strong acid versus a weak base could be something like ammonia. Similar shape, curve, but again, certain differences. So again, it will start at pH 1 because it's a strong acid. Again, you will get a shorter vertical section than you do with strong, around about 3 pH units. But this time it'll finish around about pH 11 because it's a weak base. And the end point here, the equivalence point, will be around about pH 5. We'll sometimes see this as a rule of 2. We take the strong acid, strong base, and either add or take away 2. The last one is a weak acid versus a weak base, so something like ethanoic acid versus ammonia. And this is very difficult to plot because there's too many variables, but it'll start usually around about pH 3, it'll finish usually around pH 11. You'll notice there's no real vertical section, so the only way to actually follow this reaction is to use a pH meter. You can't use an indicator because the indicator would change over too wide a range of pH units. So putting all those graphs together, we get something that looks a little bit like this. Okay, so this is them being laid on top of one another. So here we have our strong acid versus our strong base, our strong acid versus a weak base, a weak acid versus a strong base, and a weak acid, weak base. And you'll notice that they change, or their equivalence point is at different points. So this one is my strong, so that's at pH 7. And then if I have a strong acid, weak base, it'll finish about pH 5. And if I have a strong base, weak acid, it'll finish around about pH 9. And this explains why we need to use different indicators for different acid-base titrations. So anything really with a strong acid in it, we need to be using something which will change completely over this bottom vertical section. So we usually use something like methyl orange, whereas when we have a strong base, we need to use usually phenolphthalein, because then again it would change completely over this vertical section of the graph. A strong, we can use either because both of those colour changes lie on that vertical section. In the next section, we're going to have a look at why the equivalence point is different for different acid-base titrations. So we have to understand at the end of the titration what is present in the conical flask. So at that equivalence point, I've neutralized all my acid and I've not added any excess alkali. So the only thing present in the conical flask is the salt that we've made and the water that we've made. So those are the only two things which are present. But when a salt dissolves in water, the resulting solution could be neutral, but it could also be alkali or acidic. And it very much depends on whether it's come from a strong or a weak substance. So if we consider first the salt of a strong acid and a strong base, so something like sodium chloride. Sodium chloride will completely ionize in water to make sodium ions and chloride ions. But both of those ions have come from either a strong acid or a strong base. And if you remember, the stronger the acid, the weaker the conjugate base. So neither of these can react with water, therefore the pH at the end point is equal to 7. And this is why the solution is neutral at the end of a strong acid, strong base titration. The next one is the salt of a weak acid and a strong base. So this could be something like sodium ethanoate that has come from the reaction between sodium hydroxide and ethanoic acid. Again, because it's a sodium salt, it will completely ionize in water. So it'll turn into the sodium ions and the CH3COO negative ions. So those will both be in water. Now again, the sodium ion, because it's come from a strong base, will have no effect on water. But this part, the anion, has come from a weak acid. And therefore it can, because this is reasonably strong base, react with water. It only needs to be a little bit stronger than water to be able to react with it. Now notice this is a reversible sign. This is still relatively reversible, but it's strong enough that it can pick up a hydrogen ion. Remember, this is acting as a base, and leave behind an OH negative. So this is acting as my base. Let's call it base 1. This acid 1, and this is acid 2 and base 2. But this is a strong enough base to remove a proton from the water, and you get left with OH negative ions. So the salt is actually alkali. It's a good idea to learn these different equations. It's much easier to explain things in an equation rather than in words. This time we're going to look at the salt of a strong acid and a weak base. This could be something like ammonia reacting with hydrochloric acid to produce ammonium chloride. Again, that ammonium chloride will dissociate in water to form the ammonium ion and the chloride ion, and these are all aqueous. Again, the chloride ion has come from the strong hydrochloric acid, so that's going to have no effect on water, but the ammonium has come from the ammonia. It's a weak base, and this makes this conjugate a stronger acid, certainly stronger than water. So it can react with the water, force the water to accept a proton and make a bit of ammonia. But it's this bit I'm interested in. So ammonium ions are acidic because they can react with water to release more hydrogen ions. And they make an acidic salt. The last one is difficult to quantify because it's a weak acid and a weak base. Again, it will completely ionize in water. So we have my CH3COO negative, NH4 positive, and it'll give me both the CH3COO negative ion and the NH4 positive ion. Now both of these will react with the water. CH3COO negative will react with the water and produce an alkali solution, the OH negative, so that'll be alkali, but the ammonium ion again can react with water to produce an acidic solution. So you get part of the salt producing an alkali and part of the salt producing an acid. So the pH you actually end up with depends on the relative positions of these two equilibrium positions. So whichever one of these two reactions dominates depends on whether you get an alkali salt or an acidic salt, or even, if they cancel each other out, a neutral salt. So actually ammonium ethanoate is just about neutral because these two have roughly the same Kc values and they produce the same amount of acid and alkali and they cancel each other out. But that's not true for all weak acid, weak base salts. So that finishes these notes looking at buffers. And together with the pH notes we've looked at previously, that covers the rest of the equilibrium packs. So now you've studied Kc, Kp, buffers, pH, and redox equilibria. you can understand that equilibria, along with entropy, forms a major component of paper 1. So until next time, take care, stay safe. Bye-bye.